Section 7.6, I'll finally give you some values. Not finally, I only told you about the existence of quantum numbers in section 7.5. But anyway, I'll give you the values, the possible values of these solutions to Schrodinger's equation. I'll give you the potential or allowed quantum numbers, the values for each quantum number. So this is reconciling Rutherford from chapter 2 and Bohr from earlier in chapter 7. Bohr says that these electrons that are outside the nucleus, according to Rutherford's discovery of the nucleus and his revision of his boss Thomson's model, that where these electrons exactly are. Well, they're quantized, they're steps. Okay, fine. Well, what do these steps look like? Are they directional? Do they have a certain region or directionality to them? Do they only point that way in space, or are they spherical around the nucleus, like an extension of Bohr's planetary model? We'll use these values in section 7.7, so keep your notes from 7.6 handy. And I'm going to keep it in two separate sections just for the sake of not making you sit through an hour-long video. Although all these videos for this chapter are pretty short. So just a reminder, psi is that wave function is a function of four numbers. The four quantum numbers provide solutions which give us psi squared regions of space where the electron probably is. And the four quantum numbers are n, l, m, l, and ns, as I told you last time. They give the address or the seat of the electron. The principal quantum number, n, that is what it's called, the principal quantum number. AL, not LE, okay? It's not the principal like the idea of the thing, it's the main quantum number. It corresponds to the energy of the electron and directly corresponds to the distance of that electron from the nucleus. The further you are away from the nucleus, the higher in energy, the higher step you're on. It's literally like falling off of the top of a building versus falling off of a lower floor from a building, okay? The first floor is only a little bit off the ground. The second floor is even farther off the ground. Third floor even farther off the ground. It's just that our floors of our building get closer together as you go further away from the nucleus. And there you go. All right. It has integer values of 1, 2, 3, and 4. So these are all drawn spherical, but they're not all spherical. We're just talking about that a energy level of 1 is, if the nucleus is at the center here, that far away from the nucleus. And energy level 2 would be further away from the nucleus. Energy level 3, further away from the nucleus. These are 1s, 2s, and 3s orbitals because the s orbitals, in fact, are spherical. But we'll talk more about how the shapes correspond to the quantum numbers as we go on. So principal quantum number, 1, 2, 3, 4. Exactly like Bohr's model. This distance from the nucleus, this distance from the nucleus, this distance from the nucleus. Further and further away as your quantum number increases in value. Okay? Now, the orbital doesn't have to be spherical to be that average distance from the nucleus, okay? You could have a dumbbell shape, right? And take the average of the dumbbell somewhere around here, right? As that distance from the nucleus, okay? We'll talk more about that later, too. They don't have to be spherical, but it's just distance further, and further away from the nucleus as we go 1, 2, 3, 4, 5, 6, 7. Again, 7 is as high as we currently know with the current periodic table going up to element 118. There is a belief that we're going to cross some threshold and discover, or synthesize rather, because they're not going to be naturally occurring, synthesize a whole bunch of really, really heavy elements, and they'll be, you know, principal quantum numbers of 8 and higher. But right now it goes 1, 2, 3, 4, 5, 6, 7. But theoretically, you could develop solutions to Schrodinger's equation with an n higher than 7. L is the angular momentum quantum number, or the azimuthal quantum number. And the azimuthal quantum number, the angular momentum quantum number, gives you the shape of the region of space that the electron occupies. The allowed values of L are anything from 0 up to n minus 1. Okay? Anything from 0 up to n minus 1. What that means is if you have an n of 1, L has to be 0. If you have an n of a 2, then L could be 0 or 1. Anything up to n minus 1. N of 3, L could be 0 or 1 or 2. N equals 4 could be 0 or 1 or 2 or 3. Now that's as high as is currently known, but again, since n could be 5, 6, or 7, you could theoretically, for values of n equals 7, have L equals 0, 1, 2, 3, 4, 5, or 6. They're currently not known. For the elements that we have, we don't need orbitals that are, you know, those values of L, but theoretically they could exist. just for the elements that are currently known up through 118, we don't need it. We don't need it. Now, there are certain letters assigned. These are from German words. It does not correspond to spherical or dumbbell or the other shapes that I'll show you in the next section. But these shapes, which again I'll show you in section 7.7, go with these letters. So for L equals 0, that is known as an s orbital, which does happen to be spherical, as you'll see. For L equals 1, that is a p orbital. So you could have a p orbital for n equals 2, you could have a p orbital for n equals 3, you could have a p orbital for n equals 4. But you can have an s orbital for n equals 1, 2, 3, 4, 5, 6, 7, anything. Notice you can't have p orbitals for n equals 1, because that would require an L equals 1, and that's not allowed. You can't have d orbitals or f orbitals for n equals 1, because those L values are not allowed for n equals 1. The only L value that's allowed for n equals 1 is 0. Similarly, you can have s and p orbitals for n equals 2, but you can't have d or f. For n equals 3, you can have s, p, or d orbitals, but you can't have f. Once you reach n equals 4, you can have s, p, d, f. Okay? L equals 4 would be g orbitals, L equals 5 would be h orbitals. They go on up from that, but again, they're just not known. We don't need g, h, I orbitals for the elements that have currently been synthesized or discovered. So these are the values of L. Anything integer value up to n minus 1. So if I asked you, and I probably won't, is a value of L equals 6 possible? Yeah, it's possible for n equals 7, but it's just currently not known. And you don't need to memorize these, because I'll give you a big secret in a later section for how you determine what each of these things is. What each of these things are. Your choice. Next one is the M sub L, or ML. That is the magnetic quantum number. That is the direction of the orbital in space. Does the orbital point this way? Does it point that way? Does it point this way? Which way is that orbital facing if it's directional? Okay, some orbitals, a spherical orbital, would not be directional. But for other shaped orbitals, they can point in a specific direction. The values of ML for any given L are from negative L to positive L in integer values, okay? So, for example, if L equals 0, which, reminder, is an s orbital, ML has to be 0, right? Because it goes values of plus L to minus L. Well, if L's 0, ML's got to be 0. ML equals negative 1, 0, or positive 1 for L equals 1. P orbitals. There are 3 p orbitals per n where it's allowed, right? So for at least n equals 2, we can have L equals 1. And if L equals 1, we can have ML of negative 1, 0, or positive 1, meaning there are 3 p orbitals for every allowed level. L equals 2, negative 2 to positive 2. 5 d orbitals for every allowed L. 7 mLs for L equals 3, negative 3, negative 2, negative 1, 0, 1, 2, or 3. Right? 7 different values of ML for L equals 3. And that's as high as we go. All right, again, g orbitals aren't known, but it would be values of negative 3, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4 for L equals 4. But such elements are not known. All right, so from negative L to positive L are your allowed values of ML. And last but not least is electron spin. We can't have 2 electrons with the same 4 quantum numbers in any region of space, and yet we have 2 electrons per individual orbital. So, and an orbital is described by the first 3 quantum numbers, as I'll show you in section 7.6. So N, L, and ML give you the orbital. MS is gives you which direction the electrons are spinning, since there are 2 electrons per orbital according to the Pauli exclusion principle. Now we know that electrons spin based on experiment. You can take a beta emitter, or just using the photoelectric effect, getting photoelectrons, and put them in a magnetic field and see that you get 2 different beams of electrons out of that magnetic field. So we also know that, just properties of physics, that a spinning electric charge generates a magnetic field, which is why this experiment works. So an electron can spin clockwise or counterclockwise. Spin up or spin down is how we usually refer to these things. Spin up is given the value of ms, just given a value of plus a half, and ms is negative 1/2. So arrow pointing up, plus a half. Arrow pointing down, minus a half. That specific assignment isn't really that necessary. The fact that there are only 2 allowed values for ms is what's important. Plus a half or minus a half are the values of ms, and that will give our 2 electrons per orbital by differentiating them with the value of ms. Okay, here is your bottom line for that section. Oh, no, there is no bottom line for that section. That's the end of section 7.6. We'll use these 4 quantum numbers in section 7.7.